Hello everyone, this video is about chapter 12, how to calculate the result for regression. For both simple linear regression and multiple regression, we use Excel add-in data analysis to have the output result. Now, in this video, we will learn how this output result are calculated. Here is the Excel output. Let's firstly see the ANOVA part. The ANOVA is a short form of analysis of variance. This table is called ANOVA table. There are three rows: regression row, residue row, and total row. The total row is the summation of the first two rows, regression and residue rows. The first column is DF, which is degree of freedom. Firstly, we figure out the degree of freedom for the total, which is n minus 1, where n is the number of observations. Secondly, we figure out the DF for regression, which is k minus 1. K is the number of parameters, including all betas, like beta 0, beta 1, including the intercept. That is, k minus 1 equals how many x variables. If you have 2 x variables, this part is 2. If you have 3 x variables, this part is 3. Because the row of total is the summation of the first two rows, so the DF of residue is total DF minus regression DF. Next column, SS, is the sum of squares. Here, SSR is the sum of squares for the regression. Variation explained by model. SSE, sum of squares errors. Variation not explained by model. Here, SST, sum of squares total variation. So SST equals SSR plus SSE. Next column, MS, which is mean square. Here, MSR is mean square for the regression. It equals the sum divided by the degree of freedom. So SSR divided by k minus 1. Here, MSE, mean sum of errors, which equals SSE divided by its degree of freedom, m minus k. Lastly, F is a F-test statistic, which is equal to MSR divided by MSE. Significant F actually is a p-value for F-test. Now let's see the output result, this part. R-square here is also called coefficient of determination. It is how much of variation is explained by this model. It equals SSR divided by SST, which is from the ANOVA table. We use R-square for simple linear regression to determine how reliable the model is. For multiple regression, we use adjusted R-square to determine how reliable the model is, which is a bit lower than R-square. Here, multiple R, which is also called coefficient of correlation. This is the strength of the relationship, which is square root of R-square. The standard error, SE, is equal to square root of MSE, where MSE is from the ANOVA table. Now let's see this part. Under the coefficient column, these are the estimators for the slopes: beta 0, beta 1, beta 2, and so on. We can figure out how to calculate those numbers only for single linear regression. For multiple regression, we may need software like Excel to simulate the result using least square methods. Now, here is the calculation only for simple linear regression. Only one x variable. Regression equation, which is the least square line, where hat equals to beta 0 hat plus beta 1 hat times x. How to calculate beta 0 hat and beta 1 hat? Usually, we calculate beta 1 hat first. The slope, which is equal to SSXY divided by SSXX. The formula for SSXY, the sum squares for x and y, is this, and SSXX, the sum square for x, is this. Then we solve beta 0 hat by the equation. That is, beta 0 hat is summation of all the y's divided by the number of observations minus beta 1 hat times the summation of all x divided by the total number of observations. How to interpret the equation line? For every unit increase in x, the mean value of y is estimated to increase by beta 1 hat unit. If beta 1 hat is positive, it is an increase relationship. If beta 1 hat is negative, it is a decrease relationship. Given any value of x variable, we can use the estimate model to predict the value of y. For the predicted value of y using this model, we can also calculate the confidence interval for the mean value of y at a given value x, where x equals to xp. In this formula, y hat is the estimation of y given x equals to xp using the model equation, then plus minus t-score in t-table. The row is the degree of freedom, which is n minus 2. The column is the confidence level. We look at the bottom in t-table, 80%, 90%, 95%, or 99%. S here is the standard error, which is square root of MSE from the ANOVA table. And here is the number of observations. XP is the given number of X value. X bar is the mean, which is the summation of X divided by N. SSXX is the sum squares of X. We can also calculate the predicted interval for the mean value of y at a given value x equals to xp. We will notice that the predicted interval is just at 1 in the square root. So it is larger than the confidence interval because we plus and minus a bigger number. The range will be wider. Here is the plot, we can see it. The right line is the simple linear regression model line. For each value of x, we can calculate the confidence interval for the mean value of y at a given value. It should be symmetric to the straight line. The predicted interval is wider, so it is outside the confidence interval. Now, let's see how to calculate the confidence interval for the slopes. The confidence interval for simple linear regression slope beta 1 is this, where beta 1 hat, which is the coefficient from the output, plus minus t-score in t-table. Degree of freedom equals n minus 2. Then the column, we look at the bottom of the t-table. The confidence level, 80%, 90%, 95%, or 99%. The crossing is t-score. Then times S, beta hat, where S is the output standard error. We can also calculate the confidence interval for slope beta I in multiple regression. Beta is the number under the coefficient column. T here is a t-score according to the degree of freedom n minus k, where k is the number of all the parameters, including all betas, beta 0, beta 1, including the intercept. S beta hat is the standard error in the output. That's all for this video.